Hello there, grade 10. I'm going to show you a model solution how to solve this problem. Finding a relationship to describe growth and decay patterns in observed data. So we've got this data given to us with the price of a car in Hong Kong dollars in T years after it has been purchased. So the first thing to do is to take this data and create a spreadsheet like I've done here. Okay, notice that I've got column headings V and T. So pause the video and go and do that now. The next thing we're going to do is we're going to look at the differences between consecutive terms if we treat this as a sequence. So the first thing is to look at differences. Okay, now we want to do this term here, 420, subtract the previous term, press enter, and there we are, it's 80 less than the previous term, and if we double click we'll copy that formula down. Okay, now if you look at those differences you'll see that they change quite a lot. They're not always, but they're generally decreasing. So the differences are generally decreasing. This one here is going up, but the rest of them, actually some of them are decreasing, let's say. So is it an arithmetic? Let's just put a comment in there. So this is not arithmetic. Okay, now next thing to do is look at the ratios between previous consecutive terms. So this time we're going to do this term divided by the previous term, press enter, and we use a / sign for divided by, and we're going to look at those ratios. Now they're a bit hard to see, so I'm going to use this button up here to decrease the number of decimal places. There we go. Probably want a little bit more than that. I usually go for 3 significant figures. Now, I also like to click here and set all of my cell contents to be in the middle. I just think that looks a bit nicer, and also bolden up the titles there. Now, what does this tell us? Look at the ratios. What does that tell us? Stop the video and think about it for a minute. Okay, so I'm telling you that these ratios here, okay, they're not quite constant, but they're almost constant. Almost constant R value. Therefore, this is nearly a geometric sequence. But it's not perfect. But it's not perfectly so. Okay? So that's what we can tell from that. Now, let's go back to the question. So your task is to find a mathematical equation that describes the data above. Use a simple analytical method. Okay, so it doesn't want us to use technology. We're okay to use technology like this, so it doesn't want us to just plug these values into a computer and say, what is the model? That would be cheating, okay? So, but we're allowed to use technology to analyze the sequence. Now, these values here, they're pretty close to 0.8, but they're always slightly more. So what we've got to do is come up with a model, a mathematical equation or a model that describes this data. So I'm going to decide I'm going to model this as if it was a geometric sequence because it's closer to being geometric than arithmetic. Now, instead of trying to just guess the value, I'm going to work out the mean average of those ratios. Okay, we could also just have written that in as a formula, press enter, and I'm going to highlight that cell a different color, just to remind me that this is the mean average ratio. Now, why is that important? Well, because I'm going to use this in my model, in my equation. So, yeah, let's put a comment in here. Okay, I was going to try and type that, but I don't really fancy trying to type it using a computer. I'm just going to describe it, so listen carefully, okay? Now, these t values, these are all 1,000 less than the values on the sheet. Okay, so just remember that I just divided everything by 1,000 just to make it a bit easier to work with these numbers. So this is my U1, alright, this is my U1. This is going to be my R value. So remember that the general term for a geometric sequence looks like this. Oops, let's just pause the video a second. Well, it's u1 multiplied by r to the power of n minus 1. So what we'll do is we'll put that in here. Okay, so the model is going to be equal to u1, which is 500. Let's just type it in actually. 500 multiplied by 0.848, this is my estimate for the value of r, to the power of n. Now notice that we usually use n minus 1, don't we? But we don't need to go for n minus 1 because this starts at 0 rather than 1. So the first term, that's what we want. We want, when we do u1 to the power of times r to the power of n minus 1, that's to make sure we have a power of 0 on the first term. And here we have a power of 0, so that u1 is the first term. Okay, now I can copy those values down. And what we've got here, these are values which we're predicting by using those values. Okay, so by using r equals 0.848 and u1 equals 500, modelling it as a geometric sequence, this is what we get. Let's just decrease the number of decimal places. Okay, so simplify things a bit. And if we compare the model values with the actual values, so I'm going to use green for the actual values, so these would count as we're trying to model this situation. You can see they're pretty close. Okay, so that gives us some confidence that this equation was the right equation to use there. So yeah, I think that's a pretty good model for this situation. Now, if we look at differences between the model and the actual values, those would be called the errors in the model. And we can get those by looking at this cell, subtract this cell. So we're looking at differences between what the model predicts and the actual value of the car. So it's a formula, click, subtract, click. Now we could also do the other way round, v minus the model predictions, but that will do for now. Doesn't really matter too much, because what we usually do is we take the absolute value, just take the positive value of these errors, because that's really, we're interested in how close the model is and not really in what direction it's out by. So these would do for error values. We could also take the absolute value of the error, so just ignoring the sign, and this time it would be absolute value of a number of this cell here, and it will just give us the value and not worry about the sign. There we go. And again, we'll take down those decimal places. Okay, now 5. Remember that this should be divided by, these have all been divided by 1,000. So these are actually out by 5,000, 4,000, 4,000, 1,000 and so on. Let's have a look at percentage error. Now remember that percentage error is always using the actual value for the denominator. So we're going to use the v values as the denominator. The top of the fraction is going to be the error itself. Again, I'm going to use absolute value here because I'm not worried if it's above or below. And we always divide by the actual value. Multiply by 100, and there's our percentage error. Okay, again, we'll highlight and we'll reduce the number of decimal places. Okay, for 3 significant figures. So looking at that, this tells us that all of our errors are less than 2%. So therefore, this is a pretty good model. Okay, that's a pretty good model using this value of r, this value of u1, modelling it as a geometric sequence. Okay, so we've got an analytical method to arrive at the model. Check, done that. Now, questions to test how successful we were. We've already gauged the success to some extent by using these 3 columns here. So we already know that we've been fairly successful. But let's just answer the questions just to see. Really predictions because it's already passed, but they're values that come out of the model. So one thing we can do with that, we could do this. We could either just insert rows in here. Now actually I'm going to take a copy of this spreadsheet first. I'm just going to paste it in to a new worksheet, because it's going to mess things up a little bit. I'm just going to paste that in there. Now what I'm going to do is insert lines between 2 and 3 for 2.5 and in between 4 and 5 for 4.25, which is the number. There we go. So in here, come on computer, insert one above. Okay, and all we've got to do is type in 2.5 there and we're going to, we want this formula to not reference this cell but to reference the one below, so we're just going to copy that down. Okay, and I'm going to highlight that a different color just to show that it's not only a value for the model, but it's also for this sort of made up. So that's actually, we're estimating the value halfway through the second year, and if we want to estimate the value a quarter of the way through the third year, we could do this. Have to highlight the whole row, do insert one above. Now 4 years and 3 months would be 4.25 years. So we can just put that in there as a t-value. And again, we're going to copy the formula down so it references that t-value, and then we'll just highlight those columns and put them in blue. Okay, so those are answers to these two problems here. Okay, now if those were wildly different, if that number there wasn't between those two numbers, we'd start to worry. But that number is in between those two numbers, so it looks like our model is pretty good. How long after buying the car does the value drop to 150,000? Well, all we've got to do, we could just carry on here. We could take t out, so we're going to just increase t by 1. This is one way to do it, and we'll drag that down. Okay, so we're looking at 30 years, and then all we've got to do, because this is, I'm just going to copy this over there. Okay, yeah, we're just going to drag this formula down. So that formula is referencing the t column. So if I drag that down, it will just continue to reference those t values. And we're looking for when does the value drop below 150,000. There it's 158,000. Here it's 134,000. So it's somewhere in the 7th year. If you wanted to get closer, you could try putting some value in there, like 7.5. Okay, and then copying the formula down. So you're halfway through the 7th year. Oh look, and then you could even just go, okay, let's go back to 7.4, 148, 7.3, 150. Okay, so 7.3. So about a third of the way through the 7th year. So about 7 years and between 3 and 4 months, the value of the car will be down to 150,000 using that model. Okay, now how reliable do you think your model is? Well, it looks pretty good to me. I've got small errors, we've got decent looking predictions, and it's predicting into the future. Now we really have no idea of knowing how accurate these are. We have no idea, but we don't know. Okay, but that's okay. It doesn't matter. The model, we've got enough evidence there to trust that model. How accurate are your answers? Again, it's hard to say exactly how accurate they are, but what we could do is we could take an average of the errors. Okay, we'll colour that in specially so that we remember it's a special cell, and we could say that is the average error, percentage error actually. So we could use that as an estimate of how accurate are your answers. We could say, well, the average error in the model so far is less than 1%, so we can assume that any values predicted in the range of the data would have an error similar to this, so about less than 1%. However, if we go beyond the data, so once we go beyond data, we're looking at this beyond t equals 6,